And for start, I would like you to remember two small things about our company. First of all, no bosses. Everyone is like a CEO because we have a fully flat organization structure. And second thing is no offices because everybody works remotely. But today I'm going to talk about machine learning. And let's start with small quotation. Can machines think? It's a question asked by Alan Turing in 1950, specifically in his scientific paper about artificial intelligence and threats and challenges which stands before the process of the learning of the machines. And this paper is also a source of a test called Turing test. And in this test, we have some independent judge or interrogator who talks with different people and tries to guess who is a human and who is machine. And until today, no machine has passed this test yet. And artificial intelligence in practice is a subset of a broader term called machine learning. So what is really machine learning? In machine learning, we try to make machines think like us humans, to make them able to detect some patterns in data and make predictions based on them. So when machines get a lot of data, defined way of processing, cleaning algorithms, then they can handle that data even better than humans. But fortunately for us, they still need us. They need us to define that way of processing. So fortunately, maybe they won't take over the world today. And there are a few types of machine learning. There are four main groups: the supervised, unsupervised, semi-supervised, and reinforcement learning. And first, imagine that you have some examples. Example can be like a row in database. So there are some attributes, some values, and there is one unique value, which can be some type of label. So we have supervised learning. There's a label we are trying to predict, basing on other attributes. And depending on the type of this label, we're talking about classification. When this label is some type of nominal or categorical value, then this is classification. So for example, email classification to two categories, spam or not spam. And when the thing we're trying to predict is a number, then we're talking about regression. So if someone would like to predict Bitcoin prices, then it's a regression problem. And then there's another big group of unsupervised learning. And in unsupervised, we don't have such clean value which we want to predict. We are more interested in the whole processing. What is the whole output? So there is a clustering in which we just group similar objects together. But there can be different measures of that similarity, because we may group events with similar location, but also we might group things which look similar, but also we might group people with similar interests in some social network. So output of this algorithm are those groups. And when we have groups of people with similar interests, then we can target some marketing campaigns against specific people. And then there's dimensionality reduction. And in dimensionality reduction, we just try to reduce number of attributes. So let's say that you have some examples described by three numerical attributes. So it's like put points in three-dimensional coordinate system. But by doing some transformations, it may be possible to map them to lower number of attributes, to lower number of dimensions, without losing any important information. And then there's a third big group, semi-supervised learning. And in this group, you have labels, but not for all of the elements. Because labels might be expensive to get, might be hard to obtain, may require human interaction. So we don't have them for all of the examples. But still, having them only for some subset of elements can benefit the whole processing. Like in this picture, you can still guess what are the correct labels. And there's reinforcement learning. And reinforcement learning is easiest to explain based on artificial intelligence in games. So in game, there is some initial state, and there is some possible set of moves. And when AI chooses the right moves, it gets some bonus points. If it does the wrong moves get some minus points. If it reaches the goal and wins the game, gets some big reward. So it tries to maximize this. And this can be also applied to movement of robots, let's say, that robot starts in one place and tries to get to another place, but when it hits the obstacle, gets some minus points. And in the picture, you see an example related to AlphaGo, which is an algorithm for the Go game based on Google DeepMind. And it was able to beat the human Go master. And it's worth to notice that Go game is much more complicated than chess for the machines. And now, other use cases. So there's voice recognition. In voice recognition, we're talking about recognition of specific words and sentences, like all the assistants like Siri, Cortana, etc. But also this might be trying to recognize gender of the speaking person or just voice of very specific person. Then fraud analysis. So there's actually an example from Poland where government builds a system gathering all the invoices, and they want to run on this some algorithms to find some fraudulent patterns like some invalid value-added tax returns, etc. Face detection, often related to some security reasons. Ads on websites. So when a company displays an ad on a website, they want to maximize probability of clicking of that ad. So they want to profile the viewer and then match the best ad for the viewer so that he or she clicks it and they get the money. Spam detection already mentioned, for example, related to emails. And shop recommendations. So all the emails you might be getting from some shops that you might be interested in some products, or basket analysis that when you add some product to basket in some online shop and it says that people who buy this product also buys products B and C, for example. Photos description. So Google has made some algorithm where you can upload a photo and it will describe what's in the picture. Like there's a car standing near the tree, etc. But also Microsoft has done some algorithm to detect, for example, gender and age of the people on the photo. Self-driving cars related to a lot of sensors and a lot of learning. Healthcare, when you're having a lot of data, you may try to find the best way to treat a given patient. And a lot of other use cases. And now, most of the machine learning groups have the quite common learning process. But today I will focus mainly on the classification because later I'm going to show you some classification-related problem and solve that. So first of all, you may have your data located in different data sources, different data formats, and you need to gather them to the common schema. So you may have some different date formats, different time zones. You must unify them. You may have some number formats different. Some categorical variables can have different names in different data sources. So you need to unify this. And then you start the cleaning. So you look at your data and you analyze the values. And some values might be missing. So if you have a row with missing value, you have to decide what do you want to do with such row. Do you want to remove this because you can't do anything with that? Or do you want to approximate this value, to put there some average or median, for example? And on the other side, you might have outliers. And outliers are values you are sure they are wrong. So if there is some attributes which usually have values from 1 to 10, and suddenly you see there -3000, you're sure this is wrong. And you have to decide again what to do with that. Do you want to remove such row? Or maybe do you want to approximate this? And then when you have cleaned your data, you can start feature engineering. And in feature engineering, you add new features basing on other features. So you may have a field name, which would be containing some title, first name, and last name. And for some problems, it might be beneficial to split them to separate values. You might be analyzing sound files, but it's not enough just to put sound file into the attribute, but you might want to extract different sound characteristics, which might be valuable for different problems. So let's say for text analysis, you might be adding some text characteristics, some text length, and others. So depending on the problem, you add more things which you think might be valuable. And when you have prepared your data, and some people say it takes even 80% of the time of the whole process, Then you split your data to two parts, to train and test part. And you take this train part and some machine learning algorithm, and this algorithm tries to learn how to predict, in this case, labels. So it sees and tries to mimic this whole train part. And it produces some decision tree, some set of decision rules, some attributes for neural network. And then you take this model and you take the test part, but you take this without the labels. So you try to test how this model works for some new observations. And you get some predictions, and you compare those predictions with original labels, and you can calculate, for example, accuracy, so percentage, how big percent of examples was correctly classified. So you get some number, let's say 50%, and you have to decide, is it enough or not? If it's not enough, you go back. You change cleaning methods, you add other features, you change algorithms, parameters, and again until your results will be okay. And when the results are okay, then you can take model and apply new observations. So some people say that preparation takes 80% of the time, then you spend 15% of the time actually doing some machine learning, and the last 5% you just complain about date formats, etc., unifications. And now the example. So we're going today to classify conference talk abstracts into tracks. So on some conferences, you may notice that there are topic tracks like backend, mobile, frontend, etc. So I have gathered some abstracts from a few conferences. I have created a CSV file with over 100 abstracts. And it's worth to notice here that we'll be talking today about natural language processing, because we will be going to analyzing text. And for doing that, we're going to use Apache Spark. And first, a small disclaimer. So Spark is generally a big data tool. So it's optimized to run in clusters. But if your data is not big enough and you can still process this in memory, you should consider using different tools, maybe Python, maybe R language, because it will be always more efficient to analyze something in memory. And also tools which usually are aimed for single node processing offer more algorithms and more ways of cleaning. Because Spark mainly implements those algorithms which are possible to be scaled horizontally in a cluster. And Spark offers RDDs, and these are resilient distributed data sets, so you can imagine them as distributed collections. So you get some methods like on collections, map, filter, count, etc. They might be hidden underneath different structure-named data frames in your APIs, but they are distributed. And Spark is quite clever, so if one node in a cluster fails during the processing, it knows which part of data needs to be recomputed without restarting the whole processing. And Spark offers some modules. There is a Spark SQL where you can query different data sources using SQL language. There is MLib, machine learning library, which we are going to use today. Some GraphX for graph analysis. Spark streaming for stream processing with microbatching. And it offers APIs in Scala, Java, Python, and R. However, the most up-to-date API is usually in Scala, and depending on the version, for example, at some point our API had some limitations. And now let's go to the code. So I'm using today Apache Zeppelin, is a notebook. You may have heard about other notebooks like Jupyter, Jupyter Spark Notebook. It's basically a web application in which you can write some code. You can connect this to Spark cluster, Flink cluster, and others. But you can also write some markdown comments. So you can present here the whole way of thinking and processing. So you can write what are you doing, why, what methods you are using. You can write the code. It will show you the results. You can visualize them. And what is more, it will save those results so you can share this notebook later with your colleagues. And here, in the first step, I'm just doing some, sorry. I'm doing some curl to just get the abstract CSV file from GitHub to the disk. And there are some imports from Spark. And now, let's load our data. Okay, something is not working. Sorry. Interesting, it's like my keyboard is not working at all. Escape is not working. Now nothing is working. Sorry. What happened? I will disconnect for a moment. Maybe this will... Nothing works. I have to restart this, I think. First time. Those ugly machines. Yeah, so in time it restarts. Generally, we'll start by loading our data. We're going to load this to data frame using some newer Spark APIs. And then we're going to analyze it. And we're going to apply some transformations step by step to show you how the data changes. And then we're going to see results. And we're going to apply some new observations so we can see this works. It turns on. And now, generally, I'm going to apply one transformation by another. But normally, maybe you won't do that because actually this will calculate the code from scratch every time. And later, we're going to build a whole processing pipeline where everything is applied automatically one by one. Still, it turns on. Too many things turns on. Okay. Yeah, and this Apache Zeppelin I'm running here together with Spark in a Docker container. I will show you later a link, just a single container where you can just open browser and you can code. And this whole presentation together with the code is on our company SlideShare. There is a link to GitHub repository when you have the data file. Together with this exported the whole notebook with whole code. Okay, Docker is running. So in a moment, we're going to code. Yeah, one moment. And where is my code? Yeah. There's a mirroring. And okay. And it works. Okay. So value data equals. Spark is an entry point for newer APIs. You may have heard before about some Spark context, for example. Today we're using data frame, so there's Spark. And we're going to use some file, read some file with some options. So first, we have to define the delimiter because my CSV is separated by semicolons, and there's a header line with column names, so we have to define it's true. And we're rolling CSV named abstracts CSV. And let's display this file. So z.show is a function from Zeppelin, which you can use for data viewing and visualization. So you can see here that we have data set with 3 columns, label, title, and text. Like first row, label backend with title reactive streams principles applied in ACA streams. There's some text. And you can, for example, visualize the labels. So we have some backend, big data, DevOps, frontend, Java language, methodology architecture, mobile embedded, and programming languages. And now, there's one thing I haven't told you before, but most of the machine learning algorithms require to have numerical input. So we have to transfer our label and our title and text to numbers before we can process the learning. Maybe I will increase the font a bit. Okay. Do you see that in the backend? Okay. So let's say first we're going to index our labels, so we're going just to transform them to numbers. So value indexed equals, there's transformation, string indexer, and we have to define what is the input column, and the input column is the label, and what would be the output column name, let's say indexed label. We have to provide here data so that it knows all the labels, and we're applying this, sorry. So there's string indexer, value indexed equals string indexer transform data, and z.show indexed. And we see a table, and there's a new column, value 2.0 for backend. And we're going to look for another value. So there's 1.0 for big data. So it have worked. And now I'm going to define the opposite transformation, because in the end we're going to have numerical output, but it's easier for us to read the labels. So value index to string equals new index to string. Oh, it doesn't like me today. Set input column will be prediction, and output column will be prediction label. And we have to set the labels, which will be string indexer.labels. And now, we have numerical label, but we need to have numerical features. So we need to transfer title and text. And first, when you would read this whole data set, you could notice that in some cases, title is very valuable, because title may contain some technology name, and some people don't mention this inside the abstract. So let's just concatenate first title and text, and use some fancy Spark transformation for that. So SQL transformer equals new SQL transformer, and we define statement. And it's a SQL statement, so we just select all existing columns and concatenation of title space text as new column called title and text from this. So from current data frame, value transformed equals SQL transformer transform indexed z.show transformed. It's running and displaying. So there's a new column, title and text, just concatenated. And now let's split that to separate words, because words will be more valuable. So there's also transformation for that, like for everything here. Regex tokenizer, new regex tokenizer. So we say, what is the input column, which is title and text, and what is the output column, which will be words. And we define the pattern for our split. So let's say we split on every non-word character. So value words equals regex tokenizer transform transformed z.show words. Okay, some spelling. Title and text, okay. So I don't see this here. Here. So we see a new table, and there's a column words. Just there's an array of words here. But when we're looking at that word, some of them are not too valuable for us. Like there is in, at, a, and, etc. These are stop words. So these are things which won't be useful for our analysis, so just let's remove them. So there's transformation for that called stop words remover. So stop words remover, quite simple. Input column, which is words. Output column, let's say filtered. Optional, you can define the language of stop words. And value filtered equals stop words remover, transform words z.show filtered fill. And we see here a new column filtered. So in originally we had reactive streams principles applied in ACA streams. In this talk will. And after transformation, there are no stop words, so there's reactive stream principles applied ACA streams, talk, look, etc. So they are removed. So we have words, but now we have to transform to numbers. So how can we do that? We could think, for example, about whole English language dictionary. So we could build a 1000 elements array where we would put in the array position, where every array position would be related to one word. So let's say 0 in that array would mean that such word doesn't occur in an abstract, and 1 or more would be number of occurrences. But of course, we don't have here today the whole English language dictionary. What is more, this would take a lot of memory. And what is more, many technology names are not from English language, so we have to use something else. So we're going to use a small trick. So value hashing tf equals new hashing tf. And this is the hashing trick. And in a moment, I will say you what it does. So we define the input column, which is filtered, and we define the output column, which is features, and set number of features 2048. And basically, it takes every word, it calculates hash from it, and divides modulo here 2048. So it puts the words in one of 2048 buckets. So if bucket has value 0, this means that no word has fit to that bucket, and one or more are number of occurrences. And of course, we may have some collisions of hashes, so different words might be fit into single bucket. But let's not worry about that now. So value features equals hashing tf transform filtered z.show features. And we see here something new. Features. So we have expected really to see here an array with 2048 elements, because this was the number of buckets. But Spark is quite clever, and it has a different array representation for this sparse array. So there are a lot of zeros there. And it presents this as 3 elements. There's a number, which is the length. There is an array of indexes, and there is a second array of values. So this means that from position 0 to 38, we have only zeros. At position 39, we have value 1.0. Then from 40 to 147, again, we have only zeros. And at 148, we have value 1.0. So basically, this saves a lot of memory. And now, we have both numerical label and numerical features. So we can actually run the machine learning algorithm. And we're going to use the naive Bayes as algorithm which calculates probabilities of occurrences in different words in a given class. And it's naive because it assumes those probabilities are independent. So naive Bayes, And we define here something else. So features column, quite simple. There are features, and label column, which will be the indexed label. And I'm not going to run this now manually. Let's define this whole pipeline I was talking before. So we're going to do this in one step. So there are stages. And as a reminder, first we had our data, and we have used string indexer to transform a label from text to number. Then we have used SQL transformer to concatenate title and text, regex tokenizer to split text to separate words, stop words remover to remove the stop words, hashing tf to transform words to numbers, naive Bayes for learning, and this one transformation I have defined in the beginning, index to string to transform this back to label. And now we have to split our data to train data and test data. So value, data, random split, array, and let's say 3/4, 3/4, and 1/4. And now model equals pipeline fit train data, everything. And now we can use our model. So value train predictions. So we're going to check how it behaves on the part it knew during the learning process. Transform train data. And let's see how it works against examples it didn't know. So transform test data. And let's display test predictions. So it applies all the transformations. And yeah, we can see different row because it used the random split. So there's something else in test in train. So first row is here backend advanced Spring Data REST. For example, there are all of the columns we were seeing before. We see some new column row prediction related to naive Bayes and probabilities related to naive Bayes. And there's prediction numerical and label big data. So it has predicted that Spring is big data, but rather not really. And in second row, we have big data, and the talk is about Lagom. So Lagom a bit maybe touches this. But now we're not going to check one by one if it worked correctly. Let's use some automatic evaluator to get just the number, the accuracy. So there's a multi-class classification evaluator for that. And we define what is the prediction column. So it knows what it needs to compare. And what is the label column, which is the indexed label. And we define what metric we want to get, which is the accuracy. So value train accuracy equals evaluator, evaluate train predictions, and test accuracy equals evaluator, evaluate test predictions. So it predicts train set with 100% correctness, and usually this means that it's an overfit, so it has learned this data set too much, and test 72%. So not bad luck for the first try. And now let's take a look, how can we use this model to actually predict new observations. So let's define some new observations quickly. So Spark create data frame, and we define an array, and there are tuples. So I will say machine learning by example. This should work. And maybe give me some talk title. Akka HTTP. Okay. So let's say no abstract quickly. And I need to close this here. And we say to data frame, and what are the column names? Title, text. And quickly, z.show, model, transform, new observations. And we see all the columns which were created before. And what's the result? So machine learning was classified to big data, so it's okay. And aka HTTP to backend, so let's say it have worked. And now let's go back to slides. So what could we do to improve the results actually, to make the result better, here better than 72%? So of course we could have a bigger data set because 100 examples might be not enough. Thousands of examples would be better. And then there's a topic of tokenizer. So here I have just done a single split on regex. So I have split sentences to separate words. So things like big data get separated to 2 different words. But in practice, we have lost some information because big data is more meaningful than having words big and data. So we could use n-grams. And n-grams, for example, bigrams, are just like combinations where we have I will present big data topics. So we could use, for example, use both bigrams and separate words. And now, the text here was in English, and English has, let's say, quite simple grammatics. But when we're talking about Polish and all flexible forms and tenses, etc., it's a bit more complicated. So all the flexible forms with this processing would be treated as different words. Every flexible form as different word. So there are some things which we can use about that. So there's a stemming. Like, for example, Porter stemmer. It's more like heuristic. It just cuts off the different endings of the words, leaving some common beginning. So from communities and community, we get the common. So it doesn't sound like a word, but it will work. There is also lemmatization. And lemmatization is a more advanced processing, which actually uses some grammatical rules from specific languages. So it can actually bring this to the base form. So communities and community to community. TF and IDF. We have used hashing TF, and TF means term frequency. So we have here counted number of occurrences. And it means that it increases the importance of a given word if it occurs many times in a given document. But there's also other transformation called IDF, which is inverse document frequency, in which we lower the importance of those words which occurs in a big number of documents. So in case of abstracts, we could have words like talk, speak, and they won't be too much valuable here because they appear in a big number of documents. And also Spark has transformation for that. And we have used here a random split of our data to train and test part, just to 3/4 and 1/4. But we could use a k-fold cross-validation. And it's a process where you split your data to some k parts, let's say to 4 folds, and you perform 4 iterations of learning and testing. And this way, every example is once in test part. So we can test our model, our whole data set. Like every example we will have to get once correctly classified. So we get those predictions 4 times, some results, we get the average, and this way this processing is more reliable. Those results are better, but of course it takes more time because we have to run the whole process 4 times. Grid search. So we have used some magical number here, 2048. And Spark has grid search where you can provide values you would like to check together with all parameters you would like to check. And it will test all the combinations and will produce the best model. And this way you get the best model with best parameter values. Some articles and references. So first link is a Turing paper I have mentioned at the beginning. Then there is a link to Apache Spark. Third link is the Databricks companion. They offer some paid support to Spark, but they have some community platform where you can for free create an account with some online notebook and some single Spark node for free when you can play with the code. A link related to image descriptions by Google, related to AlphaGo, and Kaggle.com. Kaggle is a website with machine learning competitions where private companies post their problems and some money rewards. So basically you get the data set and you have to produce the best results. Docker Zeppelin, Docker I was using today. Spark Core NLP, it's integration of Spark with Stanford Core NLP library. It's a very good library related to natural language processing. And last link, there's a course on Coursera related to Scala and Spark. And that's all for today. If someone would like to get some stickers from Software Mill or Scala Times, for example, then just come after the talk. And do you have any questions?
As far as I understood, it's about batching processing of data we already have. How about production in such a model for streaming processing?
Well, it depends if you want to learn on a stream or do you want just to evaluate the stream?
For example, evaluate a stream and maybe apply some reinforcement learning for ready-to-use model.
So both
cases.
Yeah, so reinforcement learning would be a bit more complicated, but in most simple form. You just get here the model, which you can usually serialize. You can spawn multiple nodes, which are just stateless, only have this model. So you can scale and evaluate new cases. For reinforcement learning, those would be some other algorithms. There are some tools related to Spark, to stream processing, which offer some built-in algorithms just for the stream processing, mainly. I don't remember now the name. There's one from the Apache also. But in Spark, I don't think they have connected this yet. I'm not sure.
Okay, thank you.
Thanks, Michael. My question is how big the data really should be to justify the usage of Spark?
So if you can't process this on single node, basically, if this doesn't fit to memory, for sure you should use something which clusters. Depends what machines do you have. But basically, if you can't process this in reasonable time in single node, then you should move to cluster. But maybe you should start with single node with something else until you know what algorithm you want to use later.
That's all question?
Yeah. So if there are no questions, I'm here today and tomorrow. Just if you have something, catch me on the break. And thank you.